right, today I wanted to talk about the set of chemical reactions that make up the first half of photosynthesis, and we're going to call those chemical reactions the light reactions. So we're going to go through and give an overview and look at how these steps work and what we make and how we do this in plants. So let's start taking a look. So the light reactions are a set of chemical reactions that use sunlight to produce two chemical energy carriers. We're going to produce ATP. We've talked a lot about ATP in the past. And we're also going to produce an electron carrier called NADPH. This is a new electron carrier we haven't talked about in the past, but it works just like the ones we have talked about in the past with cellular respiration. Those were NADH or FADH2. So this is going to serve the exact same role. All right, we're going to see that the light reactions require a couple inputs. We're going to need water, and that's going to produce oxygen. We'll look at why we produce oxygen from water. We're going to see that this step is very similar to the electron transport chain that we use during cellular respiration. So there's going to be some common steps, some machinery in common, and we'll try to point out those commonalities as we go. This step occurs in the chloroplast of plants, but it uses all of the parts of the chloroplast. So it's not just in one place. For example, the proteins that are involved are part of the thylakoid membrane. And then along the way, we're going to use the stroma and the thylakoid space, or thylakoid lumen, the space inside the thylakoid. Those spaces are going to serve important roles as well. So we'll point that out as we go. Okay, so the light reactions. Let's look at a more detailed diagram of what's going on in the light reactions. So here's a chemical equation to represent the light reactions. So we're going to take some sunlight. That's going to be a source of energy. We're going to use water, and we're going to use NADP and ADP, and we're going to produce oxygen, NADPH, and ATP. So as always, on the left side of this arrow are the reactants or the substrates, the things we put into the chemical reaction. And on the right side of the arrow are the products or the things we get out of the reaction. So again, we're going to get out oxygen, NADPH, and ATP. So just as a reminder, NADPH comes in these two forms, NADPH and NADP. This molecule serves as an electron carrier. We've talked about these kinds of molecules in the past. Again, we've talked about NADH or FADH2. So for NADPH, that form is the high energy form that's carrying those extra electrons. And then NADP is the low energy form without the extra electrons. I think it's handy, the name of this electron carrier, right? We've talked about three. The only one that has a P in the name is the one that's used during photosynthesis. So NADPH is used during photosynthesis. We only use it during photosynthesis. The other two are used during cellular respiration. And again, the other two don't have a P in their name, so it's easy to keep them separated. All right, and then as always, we're going to be using ATP and ADP. Again, it's just an energy carrier molecule where ATP is the high energy form and ADP is the low energy form. So in this reaction, we're going to charge up ADP into ATP. We're going to put electrons onto NADP to make NADPH. We're going to split water in half to make this oxygen. And the source of energy that's ending up in our energy carrier molecules is sunlight. So let's see how that works. So here's a diagram of the proteins and molecules involved in the light reactions of photosynthesis. We're going to break these light reactions into two major steps. So the first step I'm going to talk about is over here. This step is an electron transport chain, an ETC. We've talked about electron transport chains during cellular respiration, and this one's going to work really similarly, but we'll point out the specific steps in just a minute. So step one is an electron transport chain. Step two is on the right side of the diagram. It is chemiosmosis. We have also talked about chemiosmosis in the past when we talked about cellular respiration. So we'll look at how this chemiosmosis is similar. In fact, this chemiosmosis is pretty much identical But again, we'll talk about those details in just a minute. So let's look at these two steps closely, and we'll begin with the electron transport chain. So here are the molecules involved in the electron transport chain. Generally, we're going to move from left to right and progress through these chemical reactions. So what's the first thing that happens? The first thing that happens is that light hits photosystem 2, we shorten that to PS2, and creates an excited electron. So that's happening right over here. Light, our little lightning bolt, hits this protein complex, photosystem 2, and creates an excited electron. So this E- is going to be excited. What does that mean though? What is an excited electron? So I think of an excited electron sort of like a tetherball. I don't know if you ever played tetherball when you were in school, but here's a little girl playing tetherball. Excited electrons have more energy. They have more energy in this way. They're sort of spinning around the nucleus of the atom they're associated with faster. So again, I think of that like this tetherball. Here, the tetherball is an electron. Okay. Light is going to hit this electron like this little girl hits this tetherball, and that impact is going to make it spin around the nucleus or the pole faster. So in my analogy, the girl is like the light. She hits this electron. So the light hits the electron, the girl hits this tetherball. And now the tetherball, the electron, spins around the pole faster. The electron spins around the nucleus faster. We've created an excited electron. A faster moving electron has more kinetic energy, so we can use that energy to do something else. All right. So we just excited this electron with this light. Now we're going to move that electron through an electron transport chain, and we're going to use the energy in that excited electron to do some work. The work we're going to do is to move an H+ into the thylakoid lumen, or thylakoid space. So again, here's our excited electron. We're going to pass it through these proteins that are part of the electron transport chain. And along the way, those proteins are going to grab a hydrogen ion from the chloroplast stroma and move it into the thylakoid space. That's sort of like how the electron transport chain worked in cellular respiration. So you might compare those two steps and see how they're similar. All right, so we've moved our electron from photosystem 2 through this electron transport chain, and now we've moved a hydrogen ion across the membrane. The next step is that that used up electron is then passed to another photosystem, photosystem 1. Light can hit photosystem 1 and re-excite that electron, give it more energy, make it move faster again. Okay. So in photosystem 1 right here, we re-excite our electron using more light energy to make our electron higher energy again. Okay. After photosystem 1, we're going to take the electron out of photosystem 1 and load it onto our electron carrier, NADP. When we add electrons to NADP, we make NADPH. So that step is happening right here. We take our electrons out of photosystem 1. They pass through a couple proteins, but they end up on NADPH right here. So we've just gone through the entire electron transport chain, starting at photosystem 2, ending with the electrons in NADPH, and we've made two products. First, photosystem 2 over here has made a higher concentration of H+ ions in the thylakoid lumen. We'll talk about how we can use that in just a second. Photosystem 1 has created NADPH right up here with its excited electrons, high energy electrons that we can use later on in another step of photosynthesis. All right, so remember when we talked about cellular respiration, I referred to the electron transport chain as being really similar to a bucket brigade. Remember, in a bucket brigade, we fill a bucket with water at one end, we hand it down this chain of people, we dump it on a fire at the other end. In photosynthesis, the electron transport chain begins at photosystem 2, so we're getting some electrons, we move them down this chain, we move the hydrogen ions into the thylakoid space, and then we re-excite them in another photosystem, and then we dump the electrons onto the fire, in photosynthesis, that fire is NADPH. So we're going to empty out the electrons at the other end onto NADPH. But what we didn't talk about was a source of electrons. So these electrons started in photosystem 2, but where did they come from? So again, here's our electron in photosystem 2. We excite it, take it out, and eventually it ends up in NADPH. That means photosystem 2 is now missing an electron. And we can't continually steal electrons from photosystem 2. We have to replace them. So the way we replace electrons in photosynthesis is we steal some electrons from water. So these electrons are going to leave water. They're going to replace the missing electron in photosystem 2. And when we take electrons away from water, we create O2 and H+. So the electron that left photosystem 2 and ended up in NADPH must be replaced. Water provides that electron, and that's why we get oxygen out of this step as well. So again, that's happening right here. Split water to make oxygen and hydrogen. The electron went into photosystem 2. So now let's look at the second part of the light reactions. We've just talked about the electron transport chain and what it produces. Now we can do this chemiosmosis step over here. Remember that photosystem 2 created this hydrogen ion gradient. We move these H+ ions across the membrane. Now there's a high concentration of H+ in the thylakoid lumen. And we can allow those H+ ions to diffuse back into the stroma through a pipe ATP synthase that we can use, and then we can use the energy of that moving H+ ion to make ATP. Remember, this exact step happened in cellular respiration as well. Back then, I talked about this step as being a lot like a hydroelectric dam. In a hydroelectric dam, water piles up behind a dam. The water then flows through a pipe, turns a generator, and makes electricity. In chemiosmosis, the water is the hydrogen ions. So the H+ is stacked up behind a dam, which is the membrane. Then we put a pipe through the membrane. That's ATP synthase. ATP synthase also contains a generator. And when we spin that generator with the flowing H+ through that pipe, we create ATP energy instead of electricity. So again, we're doing the exact same thing here in the light reactions, where the H+ that we've pumped across the membrane is like water behind a dam, and it will flow through ATP synthase. And we can use that movement to make ATP. All right, let's show this set of chemical reactions in just one more way and then we'll be done. So here's another diagram that represents the light reactions. It shows on the far left that we begin with this oxygen evolving complex. Water breaks in half into oxygen and hydrogen, and we give the electrons to photosystem 2. In photosystem 2, we hit those electrons with light, energizing them. That's why we're moving upward here. So now we have a higher energy electron. Then we let those electrons move through an electron transport chain, taking out a little bit of the energy, using that energy to move H+ across the membrane. That H+ gradient is then used to make ATP. The low energy electrons are given to photosystem 1, where they're hit by light again to re-excite them, so we get even higher energy electrons. And then we move those electrons into NADPH. We'll take those electrons out and use them somewhere else. So just as a reminder, the light reactions produce three things: oxygen as a source of electrons, ATP using the hydrogen ion gradient that photosystem 2 and the electron transport chain make, and then NADPH when we load the high energy electrons off of photosystem 1 into NADPH. So that's where we'll end. We'll talk about how we can use these products of photosynthesis in the other half of photosynthesis in another video. As always, please let me know if you have questions or specific parts of these reactions that are unclear, and I'll talk to you soon.